Welcome to my projectbazaar.com. Let me discuss about the project low rank approximation based multi-channel Wiener filter algorithms for noise reduction with application in cochlear implants. Let me discuss about the abstract of the project. Multi-channel noise reduction algorithm to further attenuate noise while attempting to preserve the speech signal of interest. Possible application for this technology include audio surveillance, identity verification, video chatting, and coherence calling and sound source localization. Features a theoretical study and experimental validation on a binaural hearing aid setup of the standard SDW-MWF implementation, where the effect of estimation errors in the second order statistics is analyzed. In this case, and for the signal target speech source, the standard SDW-MWF multi implementation is found not to be behave as predicted theoretically. Second, to recently introduced alternative filters, namely the rank 1 SDW-MWF and spatial prediction SDW-MWF, are also studied in the presence of estimation errors in the second order statistics. These filters implicitly assume the single target speech source but still only rely on a speech and noise correlation matrices. In the proposed system, the resultant of Wiener filter is given to the Butterworth filter. In order to increase the signal to noise ratio, the Butterworth filter is a type of signal processing filter designed to have as a flat a frequency response as possible in the band. It is also referred to as a maximally flat magnitude filter. Such an ideal filter cannot be achieved, but Butterworth showed that successfully closer approximation were obtained with increasing numbers of filter elements of the right values. At the time, filters generated substantial ripple in the passband, and the choice of component values was highly interactive. Butterworth showed that a low-pass filter could be designed whose cutoff frequency was normalized to 1 radian per second and whose frequency response. Let me discuss about the flow diagram for our process. First, to generate the signal. The input signal is used to voice signal. The voice signal information is converted to input data values. Thus, the data value converted to binary pattern and to given the process. The sample data to be given to the process, then to plot the sample data signal. Next, in the pre-processing stage, we filter out the noise signals, and in the noise signal stage we add the random noise to our input signal in order to make the our input signal as a noise signal. And in the multi-channel Wiener filter algorithm, extension of the Wiener theory from continuous time to discrete time is simple and of more practical use for implementation on digital signal processors. A Wiener filter can be infinite duration impulse response filter or a finite duration impulse response filter. In general, the formulation of a higher linear filter results in a set of non-linear equation, whereas the formulation of FIR Wiener filter results in a set of linear equation and has a closed form solutions. Next, in the generalized eigenvalue decomposition, where three processes are proposed, that is SPMWF, that is spatial prediction MWF. In the conventional geostatistical approaches for interpolation, the covariance structures is estimated first, and then the estimated covariance is used to interpolation. The properties of the interpolants based on estimated covariance structure are not well understood, and it is common practice to ignore the effect of the uncertainty in the covariance structure on subsequent prediction. Next, in the SDW-MWF, speech distortion weighted multi-channel Wiener filter, the SDW-MWF consists of a fixed spatial preprocessor, a fixed beamformer, and a blocking matrix, and an adaptive speech distortion weighted multi-channel Wiener filter is a structure strongly resembles the GSC, where the standard adaptive filter has been replaced by an adaptive filter takes speech distortion due to speech leakage into the noise references explicitly into account in the design criterion of the filter. Next, in the rank 1 MWF filter, it is seen that rank 1 MWF represents an intermediate approach between STWF MWF and SDW MWF and SP-MWF. And indeed, in the R1 MWF, the remainder matrix R is ignored in the spatial filter. The generalized eigenvalue decomposition is when the eigen decomposition is used in a matrix of measured real data. The inverse may be less valid when all eigenvalues are used unmodified in the form above. This is because as eigenvalues become relatively small, their contribution to the inversion is large. Those near zero or at the noise of the measurement system will have undue influence and could hamper solution. Finally, these resultant are passed to the Butterworth filter in order to improve the performance. Butterworth filter this is the first attempt to design such a functional Butterworth filters in complex W plane instead of complex S plane as conventionally done for integer order filters. Firstly, the concept of fractional derivatives and W plane stability of linear fractional order systems are discussed. Detailed mathematical formulation for the design of fractional Butterworth filter in W plane is then presented. Finally, the performance are analyzed. This system Butterworth filter performs better than the Wiener filter. These noise reduction filters are demonstrated to deliver a better noise reduction performance, especially in low input signal to noise ratio scenarios. Let we discuss about the running procedure for our process. Select the cohelia.m file in the current folder, right-click that file and run for executing this process. Here we need to select any one audio signal from dataset folder. And this is the input speech signal. Here we need to add the noise in the speech signal. This is the noise signal after we add the noises. And this is the SAW SNR performance graph for the STW MWF with EVD and generalized eigenvalue decomposition graph. And this is the graph for the eigenvalue decomposition for SP-MWF performance. And this is the rank 1 MWF performance for eigenvalue decomposition SNR graphs. And this is the noise removal by low-pass Butterworth filter. After estimate the noise from the Wiener filter, we pass that signal into the Butterworth filter in order to improve the performance. And this is the noise removal by high-pass Butterworth filter. And this is the SNR performance for entire methods. This is the filtering response and this is the input SNR in dB. For the green channel represents the Butterworth filter and this blue channel represents the SDW MWF Wiener filter method, and this is the red color and represents the SP MWF Wiener filter representation, and this black color represents the rank 1 MWF Wiener filter representation. Finally, the resultant output from the Wiener filter with Butterworth filter was processed. The simulated result can be compared with existing system. The noise reduction can be reduced as much as possible. Thank you.